So Chirudha, you are live. So you are muted, Chirudha, you are muted.
Hello everyone, my name is Chiranjeev and it is my pleasure to welcome Professor Mark Hill. A very good morning to you, sir. My colleagues and guests who have joined us today this evening. So Professor Hill will deliver the CSA Golden Jubilee Frontier Lecture as part of the CSA Golden Jubilee Frontier Lecture series. So this series was started in 2019 to celebrate the Golden Jubilee of our department. In the past, several eminent speakers have graced this occasion, and it is also it was temporarily stopped because of this pandemic. And today, it is my pleasure to announce the restart of the Frontier Lecture Series. And who better to have somebody as eminent as Professor Hill to restart the series. Only unfortunate thing is, in the past, we had a physical presence of the speaker. We will miss that presence, but I hope the online presence is what we can do today. And with this, I will request my colleague, Professor Govindarajan, to introduce Professor Mark Hill to the audience. Thank you.
Thank you, Chiru. Good evening, everyone who are in India, and good morning, Professor Mark Hill. It's a great privilege for me to introduce Professor Mark Hill. I have been given some strict orders by my junior-most colleague to do this introduction in 1 minute, which I'm going to ignore. Professor Hill is a Ginny Amdahl and John Morgridge Professor Emeritus of Computer Sciences at the University of Wisconsin. This is following 32 years of distinguished service in the Computer Sciences and Electrical and Computer Engineering departments. He serves on the Computer Community Consortium and Computing Research Association Board of Directors. He served as Community Consortium Chair during 2018 to 20 and Wisconsin Computer Sciences Department Chair during 2014 to 2017. Professor Hill is an eminent architecture researcher whose work targets computer system design and evaluation. He has made several significant contributions to parallel computer system design. Notable among them are his work on memory consistency model and cache coherence, memory system design including caches and translation buffers, simulation of parallel systems and memory system, transactional memory, and page tables and cache conscious optimization. Many of these work have significant impact in the architecture area. My personal favorites are the widely used 3C models of cache behavior, talking about capacity, compulsory, and conflict misses. The memory consistency model, sequential consistency for data race-free programs that serves as the foundation for the C++ and Java multi-threaded memory specification. Professor Hill is a highly collaborative worker with over 160 co-authors. His work has received more than 30,000 citations. He has held visiting positions in industry and academia, most recently at Google, and he mentions that as a Google intern in 2018. He has held visiting positions in Advanced Micro Devices and Sun Microsystems. In academia, he has held visiting positions at University of Washington, Columbia University, and Polytechnic University in Catalonia. He has received several awards, including the most prestigious ACM IEEE Eckerd-Mauchly Award, the highest award in the computer architecture area. He was awarded the ACM SIGARC Alan Barenbaum Distinguished Service Award in 2019. He is a fellow of ACM and a fellow of IEEE. He is a member of IISc and Micro Halls of Fame and is a co-author of 8 papers selected by IEEE Micro Top Picks. Professor Hill earned his PhD in computer science from the University of California, Berkeley in 1987, an MS degree also from University of California, Berkeley in 1983, and BS degree from the Computer Engineering Department from the University of Michigan, Ann Arbor in 1981. Professor Hill is also popular for his advice talks, targeted for graduate students, faculty, and researchers on almost everything, from attending conferences to doing impactful research, from writing successful research proposals to refereeing papers. He is also known for his vision documents. Before I hand over the mic to Mark, for the audience, we encourage you to type your questions in the chat window, which appears in the right corner. These questions will be taken up during the Q&A session. Thank you. Over to you, Professor Mark.
All right, thank you for that very nice introduction. I assume that if nobody stops me, the audio quality is good. So today I'm going to talk to you about accelerator level parallelism, and this is work that I did with Jonathan Reddy, as was just mentioned, as part of being an intern at Google. I was perhaps their oldest intern, but you know, you can always learn. Now, even though I'm centered on computer architecture, I'm going to try to do this talk to be so that everybody in computer science can get something from it. In particular, I think this level that I'm talking about is really in need of theoretical work because it has just not garnered the attention of people. So here's your chance to be seminal. All right. So I'll explain, you know, computing has done tremendous things for us, but the future holds even much more. And we'll talk about this late in the talk. One of the intentionally invisible foundations of this is technology scaling and architectural innovations, which I'll talk about. They're not really sufficient as is to take us forward to these demanding apps that require tremendous energy efficiency. There's a promising approach in mobile systems on a chip. So these are chips that have not just processors and caches, but have many accelerators. Accelerators are special purpose blocks that accelerate some part of a computation, often with lower energy. They're also called IP blocks or intellectual property blocks. And the thing that we observed on this sabbatical is, interestingly, these blocks tend to be used in parallel. And I call this accelerator level parallelism to put it in the multi-decade tradition of levels of parallelism. And this is the parallelism among workload components concurrently executing on multiple accelerators, these so-called IP blocks. And what we have now is a point success. If you design a Pixel phone or a Apple phone, you know, people can get this to work. But if we're going to use these things more broadly to enable self-driving vehicles of all types, to you know, have medical devices, to have personalized learning, we're going to need a much better science so that these things can spread more broadly. And that's what we're going to provide background for. And then we're going to conclude with a charge of some of the things you can do. So if you're coming to this question for answers, you've come to the wrong talk. This talk is really going to be about questions that I hope you will answer. So what we're going to do is spend actually considerable time, especially for this audience, on computer history to put it in perspective. I know this is out of vogue for computer scientists. We always want to know what have you done for me lately, but I think it's important to establish the foundation. Then we're going to look at this point success of mobile systems on a chip that we argue is a harbinger of what's going to happen more broadly. I have a simple model for understanding it. This is a performance model. It's not a theoretical model like a PRAM, but we're desperately need in something like that. And then I'll finish with this call to action, as I mentioned. Okay, so computing in the 20th century, computing has changed our world, and I'm not going to belabor that to this audience because you're well familiar with it. And this has required innovations, you know, theory, algorithms, applications, programming languages, system software, and it has rested on a foundation of invisible enablers. We made them intentionally invisible. We wanted the hardware for many decades to just get faster. And when you get an order of magnitude improvement in hardware, you can really do qualitatively different things. And this has happened by a combination of semiconductor technology and computer architecture. So the famous description of the semiconductor technology or transistor advances is Moore's law, which technically means the optimal number of transistors per chip or integrated circuit doubles every couple of years. And in the popular press meant that the performance of the computer system doubles every couple of years. Moore's law is having challenges, and we're going to talk about that. So if you look at this foundation, some computer architects put this slide together, so perhaps they're biased, but this is looking at a graph where the x-axis is process node, but you can think of that as a proxy for year. And then on the y-axis, we have decimal orders of magnitude of this performance metric at the fairly low level. The blue one shows you how much we're getting from the technology, and the red shows how much you're getting when you add in the architectural changes. And so you eyeball this, they're, you know, contributions sort of in the same ballpark. Okay, so how did you know, this work? So we got more transistors. So this is like you're in the happy situation where your budget doubles every 2 years, and you have to come up with fundamentally new ways to spend money. In this case, spend transistors, and these transistors are faster. So if you really want to use more transistors to go faster, it's not a rocket scientist to know you got to use the transistors in parallel. Okay, memory is a great place to use transistors in parallel. It's my bread and butter. You know, memories have gone from kilobytes to megabytes to gigabytes, and you can buy terabyte memory systems. And of course, tremendous these caches, or these transistors get spent on caches and interconnects to make the illusion that this vast memory is fast. Okay, I'm not going to talk about that. I'm going to talk about the more difficult job of using the transistors to make processing faster using the transistors in parallel. And this has not been able to use a uniform technique. We've used bit level parallelism, instruction level parallelism, thread level parallelism, and data level parallelism, all of which I'm going to define carefully in the next couple of slides, because each gave us a boost of performance, and then we built the next one on top when the prior one started to run out of potential. And I'm going to argue that the time is right for a next level of parallelism, accelerator level parallelism. Okay, so here's a cartoon of a computer system circa the year 2000. It's got a processor P at the top, cache with a $sign, bus, memory M, interface, and then devices like disks. And then to the left of that, I show these red arrows that are representing the bandwidth of communication among the layers, where fatter means that there's more bandwidth. So there's obviously more exchange of information between the processor and the cache, but than it is lower down with the devices. Okay, from the beginning, these single core or uniprocessor systems used bit level parallelism, and then we soon added instruction level parallelism. So what are these things? So bit level parallelism, when computing started well before transistors with vacuum tubes, we had very few switches. And so to do even relatively simple things, you essentially had to spread them out in time to use the fewer switches and have them take many steps. The heartbeat of a computer is called the clock, and so this would take many clocks. So for example, if you wanted to do a multiply, it would take a bunch of transistors even to produce a single partial product per cycle. So to get the final product took many cycles depending on the size of your number. As we got more transistors, though, we could use those transistors in parallel to go faster. So for example, we could build things where we can now do the core of the integer multiply certainly in one cycle, and we could even do floating point multiplies almost that fast. And some of the techniques for doing that are very tricky using redundant numerical representation, such as a Wallace tree. And this Wallace tree adds together partial products, and all the additions plus the final one do not even have to propagate a carry. And so you can go really fast. Now, the details of this don't matter, and I realize that the picture might become small, but more transistors go faster, space-time trade-off. And also, it really helped that we went to larger words. The word is the sort of most commonly used size in a computer. It went from a byte, 8-bit byte, 64, 32, and now most commonly 64 bits. And this allows us to use more transistors and have greater reach. And also the larger words are necessary in part when you use them as addresses into memory. When they're more than 4 gigabytes, you need more than 32 bits. One of the reasons bit level parallelism flourished is that, you know, even though hardware is hard, the harder part of computing is often software. You don't want to throw away your software, and these kind of changes were relatively easy for programmers to adapt to. The Wallace tree would be transparent, and the word side changes were intellectually straightforward. But you can only go so far with bit level parallelism, right? It's not really that useful to have 128-bit words or 256-bit words, so we needed something else. Oh, and I guess I forgot to mention, by the way, we're seeing an interesting reversal of this trend for machine learning with deep neural networks. While in training, there's a pressure to go down to 16-bit floating point numbers, and in inference, people are looking at very small integers, 8, 4, sometimes 1, and sometimes analog. So I find an interesting nuance to this simple story. Okay, so when bit level parallelism ran out of steam, we turned to instruction level parallelism. As people in this audience know, a simple add instruction takes many steps, including instruction fetch and retiring the operands, and then you would do your next instruction, such as a load from memory. As we got more transistors, we could start the next instruction before the previous one was finished, like putting cars through a car wash, except for the fact that instructions sequentially depend on each other. So you quickly get to a branch where it may fall through, it may go somewhere else. And so how could you keep doing more instructions? Well, we guess, and we guess really well. We guess 98% of the time or higher correctly. And we do the further instructions speculatively, and if we're wrong, we can clean up our mess. Now this picture shows us getting a factor of 5 from instruction level parallelism. Well, you know, modern processors like Intel Skylake have a 224 entry reorder buffer and a 14 to 19 stage pipeline. So they actually could have hundreds of sequential instructions up in the air at a time. And this is an impressive thing. I should note that instruction level parallelism is an old idea. It took off quickly in the 1960s. This is the first example of instruction level parallelism. It's called the IBM Stretch. And you'll notice, if you can see in the picture, it stretches to the back of the room. So this is not to be confused with a microprocessor. Instruction level parallelism took off relatively quickly because it's really completely transparent for software, unless you're getting into some super sophisticated performance optimizations. Okay, so that was bit level, instruction level parallelism. Next came thread level parallelism. Now with thread level parallelism in this cartoon, what I'm going to do is I'm going to take that single core system before, and I'm going to replicate it 4 times in the picture. And then I'm going to build this multiprocessor. And so this is not that hard for hardware designers to do. Of course, I oversimplify. However, it has a profound effect on the software model. Because with this so-called thread level parallelism, the hardware isn't so bad, but the software now has to see multiple threads running asynchronously with respect to each other, meaning that the interleaving of operations from different threads is not determined a priori. And this has taken a tremendous amount of work to try to come up with ways to make sense of this and make it easier for more programmers to work with this, with partitioning, synchronization, and managing communication in various libraries. So this is a relatively old idea, a variation, which is actually technically multi-threaded, if you know what that means. The CDC 6600 had that also in the 1960s. But unlike instruction level parallelism, thread level parallelism did not show up everywhere almost immediately. In fact, it didn't start showing up almost everywhere until the 2000s. Okay, and this was called multi-core, where you would put multiple of these processors on a single chip. This is the Intel Pentium Pro Extreme Edition. And one of the things you should know, if you, for a fixed amount of area, if you want to shorten most of the wires, you want your processor to be relatively square. And so you look at this thing and say, my God, it looks a little bit like two relatively square processors bolted on next to each other. And that's exactly what it is. Intel had a plan for a more aggressive instruction level parallelism processor, and it failed. So the fallback was to bolt two of the prior generations and then advertise performance as twice what the single processor could do. So multi-core was not this brilliant decision, but it was a forced choice. We were very concerned at the time that this forced choice would be a complete disaster because people were not ready to program parallel threads. And it turns out that even though that's true, most people don't program parallel threads very well. Some people program it really well, and many of the people who don't program it that way can still invoke where it's used in parallel. And so this has shown that there's a lot more thread level parallelism in the cloud and in the desktop and in servers. And many programmers can write like a SQL declarative query, and that can invoke a lot of thread level parallelism without them knowing about it. So we've seen an extreme bifurcation where the experts program with TLP and others use it. If you're a student in this audience, learn how to do some thread level parallelism programming so you have the option to be one of these experts. Okay, so the way computer architecture proceeds with these Moore's law and Moore transistors is eventually all these processors, as in that forced choice for multi-core, they get to go on a single chip. So the chip is represented here by this black rectangle. So we integrate them on the chip. And let me just flash some data past you. I'll provide these slides. So the top line here, this is years, and then we have various metrics going in decimal orders of magnitude. Transistors are still going up. Single threaded performance in blue has slowed down. The clock rate, how fast the heartbeat of the computer is, has topped out. We're power limited. And so what we've seen over the last 15 years is an explosion of the number of logical cores on a chip. And fully exploiting order 64 cores really doesn't happen on your desktop. It happens in the cloud and other servers. Okay, there's one last historical type of parallelism, and I'm going to call this data level parallelism. This is a level of parallelism that's been like a chameleon because it's gone by many different names. Single instruction, multiple data, or SIMD. It's called vectors in classic Cray machines. Intel calls it streaming SIMD extensions, or SSE, which is a recursive acronym. This goes back at least to the Illinois IIISc 4 in 1966. But unlike instruction level parallelism that took off fast, and like thread level parallelism, which took a long time to gestate, data level parallelism did not spread broadly until order 2010. Okay, and the broad success happened with general purpose graphics processing units, such as this NVIDIA Tesla shown here. And why is that? Well, we can't do a controlled experiment, but there's three intertwining factors. One is that the model for explaining the data level parallelism is something called single instruction multiple thread. And I don't have time to explain it, but it basically lets you sort of think like you have a thread per data item, and the threads are marching in lockstep. And it's a lot easier for scientists who are not computer scientists to understand this model than the previous models. A second reason is that NVIDIA and others spent a lot of time doing very detailed libraries. So some of the sophisticated parts of exploiting this GPU for your use case could be programmed by experts and relieving you of the burden. So software matters. And then finally, these things cost, a few $1,000s rather than a few $1 million of the previous machines. And that allowed just sort of much greater experimentation. And I'm a big believer in letting, students who are too inexperienced to know something is hard to have at these things because they can do amazing things. Once again, we've had a bifurcation of programming. Most people don't program to data level parallelism or GPUs. Some experts do, and the others benefit. I mean, so if you've ever done an image search on the web, the joke in the United States is that you're looking for cat videos. you have invoked, classification that was done with data level parallelism, even though your simple query doesn't appear to be doing that. All right, so what happened is we have discrete GPUs, and they're still discrete GPUs, but there's also a trend as Moore's law allows it to integrate the GPUs together. And that's part of the reason that AMD bought ATI, the #2 GPU company 10 years ago, and is probably the reason why ARM or NVIDIA is seeking to buy ARM at this time, to integrate these things closer together. So let's, do a history here. So let's go back to the 1940s. So this is a time when India became independent to the present day, and that's on the x-axis. And then on the y-axis, we have these various levels of parallelism. And green means that something is used in almost all computers, and black means it's had some success, but it's very much niche. It's not everywhere. And so, as I already discussed, bit level parallelism took off early, didn't get to 64 bits until the late 1990s. Instruction level parallelism took to the 1960s to have enough devices to make it sensible, but it quickly took off because it was transparent to software. Thread and data level parallelism didn't happen until this pink or salmon box. So this pink or salmon box is the end of Dennard scaling. So what is Dennard scaling? This is the less famous companion of Moore's law. And it really is what made Moore's law useful. So Moore's law said we would double the number of transistors. Okay, if you doubled the transistors and that doubled the power, you couldn't do that many times, right? Your cell phone can't keep using twice the power. A data center can't use twice the power. Well, Dennard scaling said that there were properties of semiconductors so that we could have twice the number of transistors, and each transistor would use half the power, so for roughly constant power. And that was a really golden age of being able to do transparent computer architecture for the benefit of software. With the end of Dennard scaling, we have moved into this era where we have the forced choice to thread level parallelism in the early 2000s and data level parallelism in the 2010s. So that was then, now we're now. What's next? It's the thesis of this talk is accelerator level parallelism. This currently has niche success shown in black in systems on a chip, and we argue that it should be common in the future, assuming that we do the science to make it so. So let's talk a little bit more about these SoCs and point success to see what we can learn from them. And so mobile SoCs are an interesting component in their own right, but I'm arguing that you should pay attention even if you don't care about mobile, because they're a harbinger for what can happen more broadly in energy limited systems, which I will believe is going to be all systems. Okay, so continuing on this integration thing, in some sense, these systems on a chip take the CPU and the GPU and they put it in the star field of an American flag, and then use the stripes for a whole bunch of other stuff, which I appreciate you can't see here. But it's going to be a whole bunch of accelerators or IP blocks and a bunch of fabrics. And let's go into that in more detail. So first of all, what are these accelerators? So an accelerator is a hardware component that executes a targeted computation class faster and usually with much less energy. So examples here are encryption, a hearing aid, FIR, MPEG, and some radio stuff. Okay, and this is a really old chart, but these trends maintain. And so what we're seeing here is a bunch of chips, and in blue is our general purpose processors with a certain energy power efficiency. And if you go to a digital signal processor, you can get almost 2 orders of magnitude, and with dedicated, you can get another order of magnitude. And people will debate this, but this is the potential, and this is the reason that you go through the absolute pain of trying to design and program these things. While Dennard scaling was operating, we were getting gigantic energy power efficiency gains, sort of automatically from the technology. Now we have to do work at a higher level to get them. And to see how extreme this is a Apple A12 chip from a couple years ago. The large blue square is 2 big cores, and the little square is 4 little cores. Those represent the CPUs. The rest of this picture is accelerators, including the GPU and also caches and interface logic to memory. So the CPUs have become a minority of this chip. Amazingly, this thing has 42 accelerators, and we'll see it's a culmination of a long trend. And those of you who are key science fiction buffs will know that in The Hitchhiker's Guide to the Galaxy, 42 was a key answer. Boy, as an engineer, I just don't think it can possibly be the optimal answer. So what are these chips doing, okay? So this shows an example use case. So this is recording 4K video. So you're at your wonderful holiday celebration and you're showing people eating and dancing, and you're trying to record this video. And the camera sensor at the left brings some information, and then you process things through a whole bunch of different accelerator blocks. An image signal processor twice, the GPU twice, image signal processor again, and then video encoding to then put it both, I guess, to put it to DRAM, and then there's also audio over there that has a digital signal processor operating with it. Because of the way the data is pipelined in this example, these blocks are used much more in parallel. This example is a simple sort of one-way example. Something like a more active video call, a Zoom call, is going to be much more interactive. Nevertheless, these blocks are used in parallel. Also note that the data is so large because of the size of 4K video that when you're buffering the intermediate stages, the current designers seem to have no alternative but to send things off chip. In fact, this use case has 6 round trips to DRAM, and this means that the pin bandwidth from the chip to the DRAM is going to be a first order consideration. It's not all about computation. And so, as I said, these things operate in parallel. So that's where we're getting to this ALP, the parallelism among workload components concurrently executing on multiple accelerators or IP blocks. Just to be clear, an IP block includes accelerators, and the CPU is also an IP block. So it's a short way of referring to both. So how do these mobile SoCs work? Well, you must run each use case sufficiently fast. So in the blue shows the video capture one that we just did, and it uses a number of accelerators. In this case, the one shown in green. It doesn't use the rest of the total of 42 accelerators. And that's pretty typical that you're using some of the accelerators at any given time and not all of the accelerators. And what a designer has to do is identify all the important use cases. I'm only showing 5 here: photo enhancing, video capture, etc. You got to make sure they all run sufficiently well. And it gets to be a very difficult situation to decide, how big does each accelerator need to be to get its job done for each of the use cases. And it's not easy to see this. And also what happens on these use cases is that, like I said, it's complicated time profile. So this is made up data that shows, like, in a given use case where the number of active IP blocks could vary over time. So very difficult, much more complicated than thinking about a single core or even homogeneous multi-core. Okay, so to get our head around this a little bit, BJ and I developed a model, and we're calling this Gables. And why are we developing this model? Well, if you're in the, let's say you're building a phone and you're considering buying a SoC from somebody else, which one do you use? I mean, it's not like you can port your software to somebody's digital signal processor and say, nah, it didn't work. I mean, that's just way too much work. You need some earlier numbers to winnow your search. This diversity is so bad, I was shocked to learn in 2019 that Facebook didn't even try to use accelerator blocks in their application, which, something's wrong with this picture. People are doing these blocks, and a company as well resourced as Facebook doesn't use them. How do you reason about this performance? Even harder, if you're somebody like me, you might want to design one of these things. And so you have to select what IP blocks. And this shows the history before we got to 42 accelerators. It's been monotonically increasing thus far. You have to select them, you have to size them, you have to design the uncore, which is all the interconnect and memories and such. And you know, which accelerators, how big, how do you even start with this question? So computing has a long history of having performance models. Among the more famous ones is Amdahl's law, which divides a computation into a sequential part and a parallel part. And say when you parallelize it, you can at most speed up the parallel part. Very simple, very useful. There's a good model of homogeneous multicore called roofline, which is similarly useful, and I'm going to review it because we're going to build upon it. And in general, these performance models in this sort of three-dimensional space of accuracy, effort, and insight versus something like a simulation where you do a software description of something in detail, the models give you more insight. They're much less effort to do than simulation, but they are less accurate, but they can sometimes have good relative accuracy. So models give you a first answer. They're part of the process of winnowing which you should investigate further. And so what we're going to do is develop Gables to extend roofline to be a first answer for the SOCs. And even if you don't like Gables, it gives you a way of understanding these SOCs. So Gables is going to build on roofline. So roofline takes the blood, sweat, toil, and tears of the hardware designers and boils them down to two parameters. This is the peak performance of all the cores running flat out, no synchronization problems, no nothing. And the peak bandwidth that you can take information in and out of the chip. And it doesn't make any fine distinctions about if you're going in, you're going out, you're going in bursts, etc. And so this is to represent homogeneous multicores shown by the picture on the right, where the black rectangle represents the chip and those things represent the homogeneous cores. All right, if the hardware designers were insulted that you reduce their work to one parameter or to two parameters, we're going to reduce the software to one parameter, operational intensity, or I. So this says, at least in a part of a computation, like what's the ratio of how much you use that peak performance and that peak bandwidth? So in particular, what's the number of operations you do for every byte that you bring on or off chip? Okay, so if you're streaming in two vectors and sort of adding them together in a dot product, you're going to do a sum and an add, two operations, and you're going to bring in two double precision floating point numbers for 16 bytes, and so you'll have an operational intensity of 1/8. And that's pretty low, and you're going to likely to be bandwidth limited. And then what roofline does is it then computes something called performance attainable, which is the best you can do, but you don't necessarily get there. So this is called roofline because they creatively developed a plot that looks like a roofline. So let me explain this because we're going to build upon this. So first of all, the y-axis has this performance attainable in a log scale, and one of the bounds is going to be the peak performance of the processors, which just manifests itself as a horizontal line. On the y-axis, we have this operational intensity, number of operations per byte. If you're at a relatively high operational intensity, what you do is you go from this place and you go up and you see your bandwidth limited, which you shouldn't be surprised. You have a relatively low operational intensity, like 1/2, you're going to be over here on this, what turns out horizontal line, which is the peak bandwidth on and off chip times the operational intensity. And so these two things, it's the lower of the two that determines the upper bound on your performance. So wouldn't it be nice if we could then apply this roofline to this chip with 42 accelerators? Well, we couldn't figure out how to do that, and I doubt you can do that because the chip is too heterogeneous. But if you have bad eyesight and you take your glasses off, it kind of looks like you could maybe do a roofline per IP block, accelerator plus the CPUs, and then somehow mash them together. Okay, and that's exactly what we did. Okay, and this is Gables. And so it kind of makes things look like a gabled roof. It's not going to be a simple roof line. And for those of you who don't know what a gabled roof is, there's a roof with a lot of gables. Okay, so to explain this, by the way, there's some nice simple equations in the paper. I'm not going to show equations here. My apologies to the people who like equations. So the CPU, which is going to be IP block 0, is going to have its own roofline. So it's going to have a bandwidth B0 into and out of the CPUs. It's going to have a peak performance, which is going to be this P peak for the chip multiplied by A0, and A0 is going to be defined to be 1. So we're really normalizing by the CPUs. And then for the next accelerator, it's going to have its own bandwidth B1, and it's going to have a performance A1 times P peak, where hopefully this one gives you some acceleration, so A1 is greater than 1. And this will continue for all the rest of the accelerators. And then we'll have some equations for sharing the off-chip bandwidth, and that is the hardware model. Okay, on the software side, for a given use case, like we're recording this 4K video, at each IP block, we're going to have an operational intensity sub I. Now, I know some of you say, well, that's pretty complicated. Why would you do that? Well, the operational intensities are likely to vary because in a use case, you will assign different parts of the computation to different IP blocks because they're good at different things. And then secondly, each IP block will have different capabilities for exploiting reuse, right? You need memory in that IP block, SRAM of some type, and you need an algorithm that has reuse. So these in general will differ. Okay, and then the IP, the use case will give work to each of these IP blocks, non-negative work. A bunch of them will get 0 because they're not used in this use case, and the rest of them will get some work where the F sum to 1. Now this is kind of reminiscent of Amdahl's law for those of you familiar with it, but it's different because we're going to assume the work is completely in parallel in the baseline model because that was our experience is more true than completely serial. Now you look at this and say, you know, Mark, you said simple. This doesn't look that simple. Yeah, I concede it's much more complicated, but the reason it's much more complicated in my judgment is that that heterogeneous chip is much more complicated, less that we are adding complications. So let's explain this with an example. We're going to do a super simple example that has only 2 IP blocks, so simple that you don't really even need Gables. So this is going to have IP0, which are the CPUs, and IP1, which is the graphics processing unit. The CPU is going to have a bandwidth into it of 6 gigabytes per second and a peak performance of 40 gigaops per second. The chip is going to have 10 gigabytes per second bandwidth. The GPU is going to have an acceleration of 5, so that its performance times 40 becomes 200. It's going to have bandwidth into it of 15, which is not a good design right now because that's greater than the off-chip bandwidth, but bear with me. And that's the hardware. Okay, and the software for this mythical use case is going to assume initially that we're not using the GPU. So all the work is at the CPU, so F is equal to 1, and F0 is equal to 1, and F1 is equal to 0. We're going to assume the CPU is good at caching and the algorithms permit it so that you reuse things and get a operational intensity of 8. But when we use the CPU, we're going to assume the CPU is, or the GPU is designed for streaming, so it's latency tolerant. Okay, so Gables plots look a lot like roofline, except now there's multiple rooflines. And in general, if there's a lot of IP blocks, you're going to have even more rooflines. Okay, so the purple roofline is for the CPU. It looks like a conventional roofline. The orange roofline is for memory. It's just a line. Okay, and so the way you use this, similar to roofline, is you go to the operational intensity. The average operational intensity, since we're only using the CPU, is assumed to be 8. We go up to the lowest line, that's the bottleneck, and then we go over and read the performance. And we see that the performance is 40, which is not an impressive insight from the model because that's what we assumed we would get if we were CPU bound. Okay. Roofline's power starts coming in when you try to do something about it. Okay, so obviously we're in the business of giving work to the accelerators. So let's try to give some work to the GPU. Since the GPU is 5 times faster, let's give it 3/4 of the work. So F1 becomes 0.75 and F0 becomes 0.25. So we're going at 40 and now we're going to accelerate things and go a lot faster, right? Wrong. Turns out that when we give the work to most of the work to the GPU, and the GPU has very little reuse, it uses tremendous bandwidth. Our operational intensity gets around 0.1, and our performance attainable is 1. Actually, it's 1.3. So we've gone from 40 to 1.3. We've gone absolutely in the wrong direction. So for this chip configuration, it is not a good idea to use the GPU this much for this use case. So what do we want to do if we're still designing the chip? Well, we say, well, we're limited by the off-chip memory, the orange line. Let's make that better. And I should say now, by the way, that the GPU line has shown up. That's the one in yellow. So what we can say is, let's increase the off-chip bandwidth, okay? And so let's increase the off-chip bandwidth from 10 gigabytes per second to 30 gigabytes per second. Now, those of you who are electrical engineers know that this is really hard to do. In PowerPoint, I can do it easily, but it's very hard to do. But if we do it, we're going to go a lot faster than our 1.3, right? Wrong. We're going to just go up to 2. We've gotten very little gain, and now we're bottlenecked by the yellow line. We're bottlenecked by the bandwidth into the GPU. We're fundamentally, for the assumptions given, using way too much bandwidth. And so what can we do? Well, if it's possible, what we can do is look at the GPU and add some memory in there, some SRAM as cache or scratch pad, to make it possible that there's more reuse to increase the operational intensity. Then we can change the algorithm so that it actually does this reuse. And let's say we can beef up the reuse to 8, then we can maybe get good things. And I happen to know we can also reduce the off-chip memory bandwidth from 30 to 20. Now, whether it's even possible to change the algorithm is not clear, and we need more work understanding this. But if we do all these things, it turns out we're going to be triple bottlenecked at an operational intensity of 8 and a performance of 160, which is a lot better than the 40 that we started with. Still less than the peak. You can do better. Now, I know some of you theoretical types are sitting there and saying, Mark, you know, what are you doing all this by hand? You should use, you know, convex solvers, etc. Maybe it's possible to use convex solvers today. They would have to be complemented with a cost model, you know, power model or something, because otherwise, if you use a convex solver, it would just say ratchet up everything to big numbers. Okay, and in general, I should point out that if you're using K accelerators, there'll be K+1 roof lines for each of the accelerators and the memory. Okay, so within a few months of publication, this was adopted into Synopsys's tool flow, and we'll go into the details. Let me give you 2 examples where I thought Gables really helped. These are not my examples. 2 times Gables predicted much more performance than the other tools predicted. In one case, there was a bandwidth that was assumed between 2 IP blocks, and the root cause was there was not enough buffering to cover the communication latency. So by Little's law, if you're familiar with this, and I wrote a nice blog post on that if you want, you needed to add buffers. And when they added enough buffers to cover the latency, the performance became much more similar. And this was an example where Gables basically fixed a performance bug. Another case, it turns out that the root cause was the task graph was not completely parallel like the base Gables models assumes, and that was the performance difference. And you know, it wasn't trivial to fix that, but it shed light on what needed to be fixed. And I still think that's a contribution, and maybe in the long run, some algorithmic redesign will fix that. Okay, we're not going to talk about adding SRAM for this audience. Okay, so there's a paper, there's some extensions where all the work is not in parallel. There's an interactive tool if you want to play with those Gables kind of pictures that I showed. You can get the source for Android. And this is my colleague, Vijay Janapan Reddy. And if you can see in that circle, we were running some tests on his Pixel phone and having trouble with it overheating. So we use those ice water bottles and a wet paper towel for auxiliary cooling. Because procuring anything more elegant took too much time. All right, so this is Gables. I think the key thing, like Amdahl's law, it gives some intuition in the first answer. Don't believe it too much. But we're still missing sort of the details. How do we really program this? What is the theoretical models of what's possible? And I'm going to finish by sort of talking about that. And as warned before, no answers. This is a charge to action. Okay, so computing has changed the world, but there's a lot more in front of us. I want a holodeck. If you've ever watched Star Trek: The Next Generation, this was a virtual world that you could go into. Now, this is far out, but there are better virtual worlds, like maybe we could wear glasses and feel like we're in the same room, which is more important than in an interactive situation than a lecture. I think this is really a big deal if it's made inexpensive enough. Augmented reality is very important. This is where you add information to the real world, like in this case, what package or boxes somebody was supposed to pick up to deliver out of the warehouse. But I would like something where it pops up with somebody's name and what I know about them to augment my memory. Personalized learning is a big deal. As professors know, you teach often with examples that are big enough to stretch students and not big enough to break them, both in lecture and in homeworks. It would be great if we could tailor the examples difficulty to the students. You could learn faster and not be bored, and you could not get overwhelmed, which is also learning faster. Self-driving vehicles, they've recently suffered the classic Gartner hype cycle where people assumed all problems were going to be solved in very little time, and they're proving harder, but they will be a big deal. Maybe they don't reach everywhere, but they're going to reach many, many situations. And the potential of deep neural networks to do things which heretofore required human thinking, I think is a big deal. And I know people worry about the job losses, but I think like the Industrial Revolution, it can probably move us out of the less mundane jobs to the more creative jobs. But too bad we don't have time for dinner to discuss that. All right, so computing is going to have much more demand, much more energy efficient computing. Text scaling and architecture heretofore is not sufficient. We think this is a promising approach, but it's one thing for me to hand wave and call it a promising approach. It's a lot more to figure out what are the software abstractions and things like that that make it possible. So first of all, I think we need a new theoretical model, right? I mean, great work in the early 20th century on computability and decidability required a very formal model like a Turing machine. A lot of the early work on algorithms assumed a single core processor abstracted by a random access machine, which is really what you're assuming when you say that a sort with binary comparison takes n log n time. Homogeneous multicore is, a first order abstraction is a parallel RAM or PRAM model. It's a very good model. It underestimates communication and synchronization costs, but it still is a big step. And for these heterogeneous multicores, the model we have is nothing. So why not apply your seminal ideas here rather than somewhere else? And of course, the key challenge is identifying what are the few most important things you're going to model and what are the lesser important things that you're going to leave out of your model. Let's go back to software. I regard some of this recent things as a descent into hellfire. I guess this is a more Christian concept. This shows a uniprocessor with a big P there. That's relatively easy to program, no visible parallelism. Homogeneous, parallel, where every processor is identical. It's a little bit harder, a little bit descending into hell, not that bad. In particular, because you could often take your large amount of data and divide the problem up so that each processor did similar things on different data. What if I said you weren't allowed to do that, that you had to use each of these processors for a different phase of the computation in all the data? Now, this is just a thought experiment, but this would be harder, even if the instruction set architectures and tool chains were the same. Well, the reason I'm doing this thought experiment is that's kind of the way accelerators are, except they're only worse, right? Not only do you have to divide up all the work in a task-based fashion, you have to deal with different languages, domain-specific languages often, and different software development kits. And that just adds to the practical friction. And then it's further exacerbated by the fact that these devices are currently hit under kernel drivers, which makes it hard to debug and hard to share information. So this cannot be a good end solution unless we only make these devices when they sell to the hundreds, a billion people. And what's really important here is that we got reasonable abstractions for individual accelerators. But we ain't got nothing for the whole chip. You're just good luck. Okay, I think a lesson can be learned from general purpose GPUs. It took 4 decades to really get this right, but the picture there is too small for you to see, but there's a lot of transistors doing different things on that NVIDIA GPU, but you don't have to think about it. But 10 years ago, if you tried to program these things, you had to use OpenGL. You had to stand on your head to do something general purpose. Either the CPU ran or the GPU ran. It was very coarse. You had to explicitly copy data between the CPUs and the GPU's memory. And the market didn't support much change. It was a $0 billion market. Okay, but now the situation is much better. SIMT and the software layers give you a great abstraction. You can do finer grained interactions, so you can do things where the tasks are not that big. You can avoid the explicit copies in major time, and we're seeing major returns, especially exploding because of GPUs being relatively good at deep neural networks. So what about for instruction level parallelism? I mean, the current state is not unlike GPUs a long time ago. You program each one with a domain specific language and its own software development kit, and there's nothing to help you globally. It's ad hoc. Concurrency is ad hoc. Communication, often you have to go up and down the driver stack. I showed you those things that went off chip memory. That would be nice to avoid. And how do you design and select? There's no great guidance. And so we really need to move to a world where we can come up with an abstraction for these SoCs that people can program to, some kind of like streaming data flow. We want to have better support for scheduling. GPUs, by the way, CPUs just have like interrupts for scheduling in hardware. It's all done in software. GPUs have a symbiosis between software and low-level hardware for how to do it. How should we do the communication? Should there be something like Q pairs, if you know what that is? Should we move to a model like in networking where there's a control and data plane? All these questions are open, and we certainly need tools and CAD tools to accelerate this. So there's lots of challenges, but especially in research, you should view these as opportunities. I mean, for programming, I do think we need a global or runtime model. My current favorite is some kind of directed graph of streams among the IP blocks, but I could be wrong. For concurrency, we want to be able to schedule, and in some cases when blocks are used by more than one entity, we want to be able to partition and virtualize. The communication is a big question. Caches, my bread and butter, were the correct answer for CPUs with very unpredictable memory referencing patterns. They may not be the right answer here. And designing, when do we design similar accelerators? Do we combine two things? That saves area, that saves cost, but then each of the accelerators might be a little less good at their individual task, costing a little power. So how do you trade this off? So Hennessy and Patterson in their Turing Award lecture a couple of years ago said that we are on the verge of a golden age of computer architecture. I would argue that we are on a golden age of computer science. And thank you.
Thanks a lot, Mark. It was a great talk, and I can see that many of the questions are lining up. But before we get into the Q&A, I would like to request Professor Narahari, who is the Dean of Electrical, Electronics, and Computer Sciences Divisions at IISc, to say a few words. Over to you, Professor Narahari.
You want me to stop sharing?
Yeah, sure, Professor. Thank you, Professor Mark Hill for a fantastic golden talk in the Golden Jubilee celebrations of the Department of CSA. In Indian cricket, we have two innings, the first innings and the second innings. We had wonderful frontier talks in the first innings, and we have today provided a brilliant start to the second innings of the Golden Jubilee Frontier Lecture Series. Thank you for a wonderful talk. I hardly know anything about computer architecture, but even I understood what accelerator level parallelism means. Thank you for spending your precious time with us and for inspiring the grad students and the faculty members with this excellent talk that you have given today. Thank you also for gifting us Arka, who continues to do stellar work, the kind of work that he started doing with you. Thank you so much for this very precious gift to us. As a very small token of the CSA Golden Jubilee celebrations, we are honored to present to you a silver plaque, which I request Professor Govindarajan to show to all of us by sharing his screen. Here is a silver plaque, which you will have to receive virtually now. Please receive it virtually. We will send it to you by courier service very soon. The plaque says Department of Computer Science and Automation, presented to Professor Mark D. Hill for delivering the Golden Jubilee Frontier Lecture of the CSA Golden Jubilee. Thank you so much for delivering this wonderful talk again. I should use this occasion to thank many people who have made this a success. I must thank Arka, Govindarajan, Chiranjeev Bhattacharya, Vinod Ganapati, and Siddharth Burman for taking care of all the logistics, and also the Computer Science and Automation office staff for taking care of all the arrangements. We would like to thank all the audience for their participation and the wonderful questions that they have already posted on the chat box. And thank you again, Professor Hill, and thank you again and again. Thank you.
Thank you very much. That looks beautiful. I want to mention, though, I have to thank the country of India for gifting me Arka temporarily. He is one of the reasons why being a professor is a true joy. So I'm happy to return the favor and deliver him back to you.
Sure. Thank you very much. Thank you so much.
Thank you, Mark. Like, it made my day. Thank you. So we have few questions lined up for you, Mark. So Alvin asked that is reconfigurable computing is viable alternative to having lots of accelerator, because you won't be using all the 42 accelerators simultaneously. So what's your view on that?
So, I mean, of course, the final answer gets determined by engineering constants. I think with many questions in engineering, extreme answers are not the correct ones, but it's likely a mix. I see it likely that reconfigurable logic becomes like one of the accelerators, or maybe in the big accelerator or multiple accelerators, that you'll still use fixed accelerators for things that they're really good at, but reconfigurable, it's sort of theoretically a little less good, but it's more flexible. And that's going to be particularly important when you have use cases that are changing, which is definitely true. That, when you start building a silicon chip and then you go through the process of designing, fabricating it, putting it out into a system, and then the users use the system, there's a big time delay between when you configured you designed the original hardware and people use it. And so having some of the chip be available to anticipate this is a good thing. Obviously, you can always also anticipate it with the CPU, but CPUs are falling off relative to these accelerators. So I certainly see that technology is important, but it also depends on how well the fabrication technology allows you to integrate, a given reconfigurable fabric with the rest of the system on a chip. Let me just raise one more thing. Tool chains are critically important too, right? If what happens is you can write most of your stuff in software, but for the FPGA block, you write Verilog. That's going to be less useful than if it's somehow integrated so that it looks like a flexible accelerator, like and while the others are fixed accelerators.
Okay. Thank you, Mark. So the second question is from Professor Jayant Harit Shah. He asked that you used DRAM model in the talk. So would any of the parallelism options would change in the NVM when you have NVM in the mix?
All right, that's a very good question, and I by the way, I'm very interested in NVM. Wrote several papers recently. So the model that I did was at a sufficient hand wave. It was really modeling the bandwidth off the chip as a single number. Didn't even pay attention to the latency. And so if you switch to NVM, that would change the latency, not currently modeled. And it would change the bandwidth number, but the model will still work. So I don't think that change doesn't really matter for the model. What it really matters for is the real software. I think you need to be able to tolerate that greater latency unless there's sufficient locality that you either have some other DRAM that's part of the memory or you have a large SRAM cache on chip. So it's definitely going to change things. To me, the biggest that NVM is going to do is that you're going to build systems that can take quick power naps, right? If you can get your states to knock off memory, you can go to sleep for a second while the display is still running, and you can reduce your actual power consumption without any visible seam to the user. And I think that's a pretty powerful thing. It's not really viable to power down DRAM. Okay,
so we have a question from Professor Govindarajan. So he asked that you talked about a computational model for accelerator level parallelism, but computational model like in a PRAM, LogP were useful for analysis, but not necessarily for developing software. So how do you make the newly proposed model useful for both the analysis and possibly for the software development?
Well, that's a good question. I think there's different models at different levels. I spend time in my parallel architecture class, Arca may remember, but I spend time on the PRAM, right? And even though you don't use it directly, I think it just gives you some sort of insights on sort of what's possible and what's not. So I think what we need first is a model that gives you sort of insights on how to think about the chip, even if you can't use that model directly. I mean, for example, with the PRAM model will tell you the way to do a matrix multiply is you start out with a number of processors related to the number of elements in the matrix, n squared processors. And clearly that's sort of wouldn't work in practice. It would be very slow and not so feasible. But yet the model is pretty useful. So maybe someday you can do a model that both gives you some theoretical bounds and tells you how to program it, but that's a pretty high bar. Let's start with doing models that do those two things separately.
Okay, thanks. So next question from Bishwa Panda at IITK. So he asked that any comment on processing in memory and how it would affect ALP? How does Gables model will change if you have processing in memory?
That's a good question. I haven't really thought about it. I guess the right thing to say is, Gables is, a model for an SoC with external memory. And if you have a different situation, you should use a different model, right? So we can throw away Gables, maybe get some insights from it. I think the real question is, how does processing and memory change the way you do computation, and why is it talked about now, why it's failed many times in the past? I think the reason it's talked about now is, well, first of all, in the past, conventional computing was going ahead so quickly, it was like a snowplow discarding everything else. And now conventional computing, like a single-threaded performance, is not improving that fast, so many more options are viable. That's one thing. Second thing, when processing memory works really well is when you have sort of asymmetric data. Like there's this gigantic corpus, and then there's this small query, right? And you can move the query, you can broadcast the query to the different shards of the corpus. And that paradigm has really shown up quite a bit these days, from anything from internet search to recommender systems. Whereas in the past, a lot of times you were taking, two big pieces of data and wanting to combine them. Well, you got to bring them, one of them has to move, and so you may as well bring them both into the processor. And so I think that's another reason. And then a final reason is that I'm not convinced that processing actually on the memory chip is the right thing, but processing very near memory is looking pretty interesting, right? So if you have a hybrid memory cube where you have a stack of DRAM chips and below them you have a logic chip, that is, that's a very viable technology, because the logic and the DRAM get implemented with different processes, and the bandwidth from that chip up the stack is tremendous, and so it's a lot like processing in memory. And for those reasons, I think that we're going to see this. I can't guarantee it's going to succeed yet, but it's going to be explored extensively for good reasons.
Okay, so another interesting question from Uday Reddy, faculty at IISc. So he asked, could you comment on the kind of balance that we may see between the number of cores, accelerators, cores per accelerators, and the SIMD width of each of those cores, including, say, two-dimensional SIMD. So are you going to limit the SIMD width and have more cores, or limit the number of cores and have wider SIMD in those cores?
Okay, excellent question. So there's a slide that I used to have that showed a lattice of how these various levels of parallelism are related to each other qualitatively. And so a thing that I failed to emphasize in this talk, right, is when we move to accelerator level parallelism, as the questioner points out, inside of each of these IP blocks, you're still using these other levels of parallelism, right? The CPUs, are you going to use the thread level parallelism? They may use the data level parallelism. They certainly lose instruction level parallelism and bit level parallelism. And so how these levels of parallelism play out, I think that's going to depend on somewhat on the hardware constants, but much more on the software properties. And we already saw this happen with processors, right? When you only had one processor, the processors were getting fatter and fatter and fatter and fatter. And then suddenly when we had to turn to multi-core, you didn't take the fattest processors and do a few number in the multi-core, but rather you went to something a little bit more modest. However, the software was such that you didn't want to go to really wimpy processors and have many of them, and to some extent that was done by Sun Niagara, and that was only medium successful. So I'm not answering that question because it really depends. But I think what you've pointed out is a really something that has to be investigated sort of in detail to come up with good answers. How these levels of parallelism interact with each other.
Okay, so we have an interesting philosophical question where one asks that Ashish asks that typically in a mathematics or any other theoretical field, if somebody proposes a theory that is either universally accepted and until someone actually proves it wrong, or propose another concept that supersedes it. But in computer system, most of the concept change from, yeah, say architecture to architecture. So, how are such cases handled considering the efficiency and validity of the research content? Maybe the question more is, what is true in architecture today, could that be true tomorrow? And how the model, captures that changes that keeps continuing. It keeps continuing to happening in architectures that we design.
Right. Okay. So first of all, I make no claim that the Gables model is going to, be decades long lived. So let's see. You want to be philosophical, huh? So abstractions in mathematics are perfect, right? Once you say this is what a matrix is, and then you start proving properties of matrix, it absolutely holds for all matrices forever. Okay, abstractions in engineering, any abstractions of the real world are approximations, right? You've learned about the particle and wave model of light when you were in school. I remember being frustrated by this in high school and asking my physics professor, which is it? And he said they're both models, meaning they're approximations. And so the things that we do in computer science, especially when you get lower into the practical systems, they're always approximations. And so, the property of an approximation is the famous quote that I like, all models are wrong, some are useful, right? And so the question with a model is, are we capturing, what a model tries to do is capture what's most important. And to be a useful model, it also has to discard what's less important, otherwise it doesn't simplify. And what's important or not important can change, and so the model can, does not stand the test of time like properties of eigenvectors do.
Thanks. I think we are running short of time, so I'll take probably this is the last question. I know there are more questions lining up, but we are running over. So one more question, this might be of interest to you, is that there's a question from Jay from IIT Tirupati, is does the memory model, I believe this is the memory consistency model he's referring to, play a role in deciding the peak bandwidth while doing the Gable?
Okay, so well, I'm glad you asked about memory consistency models. It gives me a chance to do an advertisement. One slide that I didn't show is that I have a new edition of my book, a primer on cache coherence and memory consistency, and we paid for open access, so all of you can download it for free anywhere. So that's a shameless pitch, which I will not make any money. The memory consistency model is a detail, a finer grained detail that is captured by the Gables model, right? The Gables model doesn't even say whether you're using shared memory or message passing, within your SoC. It's just looking at the bandwidths of and computational abilities. So it's very much, for those of you who took some other modeling, it's really bottleneck analysis. So the memory consistency model is important when you get down to the questions that I had in the last part of the talk about, like, how are you going to program this, etc. But it doesn't. It's part of the part that was deemed not the most important when we did the Gables model.
Okay. Okay. Probably this is okay. This is really the last one. Okay. So we'll be short. So there is this one other question, is that what's your opinion on CPUs supporting various domain-specific extensions, like, say for SIMD, vectors, or for cryptography, versus pairing the CPU with multiple accelerators? Any comments on that?
Okay, well, that's what you said. There was a simple question. That's not a simple question. So the advantage of putting something into the CPU is that you can invoke it at really fine grain, maybe with an instruction, maybe memory mapped, but implemented close by, and you can get information that was already at the CPU from, like, say, level 1 caches. The disadvantage of putting it into the CPU is that it sort of bloats the CPU, and that it requires you to use the CPU memory system such as it is. So an example of that, I mean, Intel has for a long time tried to do these streaming SIMD extensions and have you use that rather than a GPU. And, you know, oversimplifying a little bit, that hasn't completely succeeded. And in my opinion is because it bloats the CPU a lot, and the streaming SIMD extensions really want streaming memory, and the caches on a CPU are really about, you know, latency reduction. And so there's a bit of a mismatch. And so it's, you know, I sort of believe that for data level parallelism, you know, having a separate thing makes sense. So I think that's a simple, smaller things that need to be invoked at fine grain, getting small amounts of data, it makes more sense to put in the CPU. Remember, at one time, the floating point chip was separate from the CPU chip, and it made a lot of sense to integrate that. That happened a long time ago. By the way, Uri Weiser has a nice paper called something like Beware the Valley, which talks about CPUs versus GPUs basically, and why he thinks they should stay separate. I can send Arca the reference if people are interested. It's got some nice math in it too.
Thank you very much, Mark, for your valuable time. I think this is a lively discussion we had, not only the great talk. Thank you very much. So for all in the audience, thanks for, I know this is a little bit late in Indian time, but for staying back and asking great question. Thanks a lot. And Mark, you have a students meeting as well. So yeah, following this
another link, I'll get on it in a couple of minutes.
Yeah. Oh, sure. Thank you very much. Thanks.
Next time dinner is on us. Next time dinner is on us.
Yeah.
Thank you. Bye bye.
I want some sag. I love sag.
Oh.
Yep.
Aloo gobi and bengal bharta.
Okay.
Sure. Thank
we'll
you.
have them here. Thank you. Thank you. Yeah. Bye.